Hello and welcome to my talk. My name is Sara Konrad. I'm a researcher at the Excellence Cluster Structures and the Institute for Theoretical Physics at Heidelberg University. I present my analytical work on universality of structures from the small-scale limit of the dark matter power spectrum. The theoretical framework we're working in is kinetic field theory, so let's get into it. One question that we ask in cosmology is how do structures grow? So for example, we have the cosmic microwave background with its tiny temperature fluctuations, from which we know that the density fluctuations at the time of recombination were pretty small. On the other hand, we can observe today galaxies, galaxy clusters, the whole cosmic web with its pronounced structures. Now we would like to understand how the dark matter went from these tiny density fluctuations at early times to the structures we can observe today. So as I already mentioned, I work in the theoretical framework of kinetic field theory. Kinetic field theory is a statistical field theory for particles in classical phase space. And here comes your KFT 101. So the ingredients of kinetic field theory is the full 6n-dimensional phase space of classical particles. So very similar to a computer simulation, we have for every particle a position q and a momentum p. We need initial conditions, so a probability distribution for initial positions and initial momenta. We need particle interactions that govern the dynamics. And we need to take into consideration the expansion of space-time. Particle interactions and the expansion of space-time are encoded in a Hamiltonian, which govern the classical equations of motion. And by that you can really imagine we start with a probability distribution in phase space initially, transport this in time, get a probability distribution phase space at a later time, and can derive statistics of the density field from this. So we construct a generating functional from the free motion and have an interaction operator similar to quantum field theory where we encode the interaction Hamiltonian. We then have operators that act on the source field of the generating functional to generate average values of our field values, which are the coordinates. So the 6n-dimensional phase space for our dark matter particles are considered to be the co-moving coordinates. As initial conditions, we assume we have a Gaussian random field for the density, from which we perform Poisson sampling to generate the positions of the particles. Particle interactions are encoded in the Hamiltonian, where we choose free motion and encode the gravitational potential from all the particles in the field in an interaction part. We choose as time coordinate the linear growth factor. And with that, we get the first order particle motion, which is that the position of a particle at a later time t is simply given by the initial position plus the time coordinate times the initial velocity. Note that by choosing the linear growth factor as a time coordinate, we already implement large-scale interactions into account, and the trajectories we get are equal to Zel'dovich trajectories. So we are interested in the statistics of the cosmic density field. And by that, the easiest way to do that is to look at the power spectrum. In our case, as I said, the first order motion in kinetic field theory is equal or similar to the Zel'dovich approximation. So the first order power spectrum is then similar to the Zel'dovich power spectrum, which is the average over e to the ik times the difference of particle positions. In kinetic field theory, this becomes a prefactor, which contains an exponential damping, and a highly oscillating integral. The functions here in the exponent are linear in the initial power spectrum and encode for the initial correlations. Note that the exponential damping is governed by the sigma 1 squared, which is the first moment of the initial power spectrum. So how does the Zel'dovich power spectrum look like? Here you see in purple the Zel'dovich power spectrum from kinetic field theory, and in gray the linear power spectrum. You see that we introduced a cutoff, and I will talk about this in a second. First, let's look at the large scale limit, so the small k limit. The large scale limit is described by the linear power spectrum times this exponential prefactor that I showed you before. The reason for that is that we can expand the oscillating integral for small k and we get the linear power spectrum. So by that we can quantify up to which scales the Zel'dovich power spectrum is very similar to the linear power spectrum. This is governed by this exponential factor, and you see that as time progresses, larger and larger scales become nonlinear. We call this the linear regime. Now let's look at the other end of the spectrum. We found, and this has also been found by others, that the Zel'dovich power spectrum attains a k to the minus 3 tail for large k. And now note that this k to the minus 3 tail is universal, regardless of the shape of your initial power spectrum and the amplitude. So with whichever power spectrum you start, you will end up with a k to the minus 3 power spectrum at first order in kinetic field theory, as in the Zel'dovich case. Now, we would like to know up to which scales this k to the minus 3 tail is valid. We can estimate this k by going one order higher in the asymptotic expansion, which gives you a k to the minus 5 term, and at the position where the k to the minus 3 and the k to the minus 5 asymptotics intersect. Now we call this regime the regime of universality, because this power law indicates some universal features in the structures that are below this scale. And because this is a universal feature for all power spectra. With that, we can divide our power spectrum into 3 parts. At large scales, we have the known linear regime, and at the very small scales, we now have this asymptotic regime, which is universal. The intermediate regime is kind of the bad one, because here very highly nonlinear things happen. We know that the transition from linear to the bad regime is the mildly nonlinear regime, and at the transition from the bad to the universal regime, we know that our asymptotic expansion will break down. So we will exclude now the bad regime for now. We will not look at the linear regime where we know what happens, but in the following we will look at this universal small-scale regime. For this regime, we derived an asymptotic expansion that contains all the terms. So we have an expression for all the terms of this asymptotic series. We see that it decreases with odd exponents in k. We will now have a closer look at the k to the minus 3 asymptotic amplitude, because we assume that this governs the time evolution of small-scale structures in Zel'dovich. We found an expression that depends on time and sigma 2 squared, where sigma 2 squared is the second moment of the initial power spectrum. Plotting this against t squared times sigma 2 squared, which we call free streaming time, we see that the amplitude first rises, attains a maximum, and then decreases. So why is that rise and then decrease? Let's look at a simulation of a density field that consists of individual particles which are on Zel'dovich trajectories. So at early times, when we start from a Gaussian random field, we see that we create structures that look very similar to the structures in the universe. This is because particles are attracted by the large-scale field. They create structures, but at some point the particles cross, so they reach a maximum in the structure amplitude. And after the crossing, the structures will re-expand because they are not kept together by the small-scale structures in the Zel'dovich Zel'dovich approximation. This is why we exclude this late time and we focus on early times up to the point at which the particles cross their trajectories. Now note that this crossing of trajectories in the particle picture is more a collective effect than really a crossing of individual streams. This is something I really want to emphasize. So at small scale stream crossing we find that the amplitude attains a maximum which is universal. So this amplitude of approximately 55 is reached for any initial power spectrum, regardless of the shape and regardless of the initial amplitude. Now let's look at the time at which this maximum amplitude is attained. This time is highly cutoff dependent, and you see that when sigma 2 squared is larger, this time is reached much earlier. So the more small scale structures we have initially, the faster this maximum amplitude is reached. So what does this mean? We find that a maximum amplitude in small scale structures is reached. This depends on your cutoff, the initial power spectrum. And now let me remind you that the cutoff in an initial power spectrum or linear power spectrum is directly related to the mass of potential dark matter particles. So by analyzing the stream crossing time, we might get hints on the mass of dark matter particles, if dark matter is a particle and if it is thermal, of course. So let's have a closer look at that. So in the following, we look at scales directly related to this small scale stream crossing. So this collective effect of stream crossing, which we define by the small scale amplitude of the power spectrum being maximal. Now let me emphasize that we don't assume that the power spectrum in a Zel'dovich approximation is the correct power spectrum at small scales. What we assume is that the scales that are already imprinted in the Zel'dovich approximation, because large-scale gravitational interactions are already taken into account, that the scales that we can derive now might have some meaning also when more interactions from the small scales are included. So let's have a closer look what scales we were looking at. First, we looked at the redshift at stream crossing as a function of the cutoff in the dark matter power spectrum. And what we were wondering now is at which times might this stream crossing redshift be most important. So let's rephrase. The small scale stream crossing happens when small scale structures are the strongest, maybe for the first time. So it would be interesting to see if maybe at the era of reionization this coincides with the small scale stream crossing redshift. So we looked at the redshift at stream crossing as a function of dark matter cutoff, and we marked the stream crossing redshifts at which reionization probably took place, which is approximately between 6 and 20 as a wide range taken. If we assume that the small scale stream crossing happened during reionization, so during a phase transition in our universe where small scale structures became very important to form the first stars and reionize the intergalactic medium, we can now deduce which dark matter cutoff would be most likely. And we find that the cutoffs in the initial power spectrum correspond indeed to warm and cold dark matter. What we found is that under the assumption that small scale stream crossing happened at the regime of reionization, we deduce that warm dark matter and cold dark matter are highly plausible models for dark matter. Now we can also deduce length scales and from that mass scales that depend to this era. So what we now see here is mass scales at stream crossing. Now we look at the mass scales that are most plausible with the cutoffs that we get from the reionization small-scale stream crossing hypothesis. If we now mark again the cutoffs that correspond to reionization, we see that we get mass scales from below solar masses up to 10 to the 10 solar masses. Now this is indeed a mass range over many orders of magnitude. However, if we look at the colder regime of dark matter, which might be for some of us the more plausible ones, we see that we are in the mass range of below solar masses and 10,000s of solar masses. So this is also an interesting mass range because this might be corresponding to the masses of the first stars. So by the hypothesis that the Zel'dovich approximation yields scales that have some meaning, by the hypothesis that small-scale stream crossing might be related to reionization, we find plausible values for the dark matter model, and we find mass range that correspond to the first stars. So let me summarize what we went through. So first of all, I've shown you that kinetic field theory can be used without extensive assumptions to investigate the universality of cosmic structures. We find a k to the universal k to the -3 power spectrum in a Zel'dovich approximation, and what I haven't shown you, but what we also worked out, is that in a near field approach where you include more interactions, you also get the k to the -3 tail. These results are independent of your choice of the initial power spectrum. However, the time evolution of small-scale structure is highly sensitive to the initial power spectrum, especially to the cutoff, and by that to the model for dark matter. If we consider small-scale stream crossing as a collective behavior where small-scale structures are maximized, and we relate the scales that we can derive here to reionization, first-order kinetic field theory predicts time and mass scales for warm dark matter and cold dark matter that are indeed related to reionization. And with that, I thank you for your attention, for visiting my talk, and I thank Matthias Bartelmann, the Bartelmann Group, and Jonadav Bareginat from University of Oxford for great collaborations. And of course, I thank my funding. And with that, thank you, and I'm looking forward to interesting discussions.